Hey there, in this video I'm going to just show you an example of how to solve a system of 3 equations with 3 variables. Our goal is to get rid of 2 of these x terms, any 2 of these x terms, and then to get rid of one of the y terms in one of these 2 equations. So let's start with looking at how we can get rid of one of the x terms. I'm going to multiply this equation by -1 and add it to this equation, because then the x terms will drop out. So the way that I'm going to have you do that is we're going to just multiply that equation through by -1, which gives me -1x plus 2y plus 3z equals -2. So when I do this, the equation that's not involved in the transition, which is this top equation, this needs to stay. So I'm going to write it down over here as 2x plus 4y plus z equals 1. Now what I'm going to do is I'm going to add a multiple of this equation, which is what I have in red, to this equation. Now, one of these 2 equations needs to stay, and I can choose which one that is. So I think for this example, I'll just leave the second equation as it is, x minus 2y minus 3z equals 2. And now I'm going to replace this equation with the sum of this equation and a multiple of that second equation. So when I add those together, the x terms are going to drop out, and I end up with 3y plus 2z equals -3. So what I've just done is now I have a blank right here. So now I need to get one more blank. So I need to work with these 2 equations to get rid of one of the x's. Now it makes the most sense to multiply this row by -2. So when I do that, I'm going to write the -2 out here, and I'm going to go ahead and multiply through, and I get -2x plus 4y plus 6z equals -4. So what I did is I multiplied -2 times all of the terms all the way through. Now, as I said before, the equation that's not involved in the transaction, which would be this equation, it needs to just stay there. So I'm going to write it down as 3y plus 2z equals -3. Now, I also need to leave one of these 2 equations in my system. Now, I'm going to use this one instead of the top one simply because it has a coefficient of 1, and that's going to be a little bit easier down the road. So I'm going to leave that one, and I'm actually going to put it up at the top because I can put it in whatever order I want to. So I'm going to leave that one, and I'm going to put it at the top. Now I'm going to replace this row with the sum of this red equation, which is a multiple of the second one, and I'm going to add that to the top one. So when I do that, the x terms are going to drop out, and I get an 8y plus 7z equals -3. So what I've done is I've added the -2x to the 2x, that's 0, the 4y and the 4y, that's my 8y, the 6z and the 1z, that's my 7z, and the -4 and the 1, which is my -3 right here. Okay, so now what I've done is I've got a blank space here and here. So now I need to take these 2 equations, and I need to get rid of one of the y terms. This guy's done. I'm going to leave him alone. I'm not going to mess with him anymore. But I'm going to look at these 2 equations, and I'm going to get rid of y. And to do that, I'm going to multiply the top equation by -3 and the bottom equation by a +8 so that I will have opposites. So I'm going to write those down here. This is going to give me -24y minus 21z equals a +9. For this one, I'm going to get a positive 24y plus 16z equals negative 24. Okay, so now I have my top equation, which is not involved in the transaction, so it'll stay. And I need to leave one of these two equations here. I'm going to leave the one with the smaller numbers. So that would be the 3y plus 2z equals negative 3. It really doesn't make a big difference. You can pick either equation. And now for the third one, I'm going to put the sum of these two equations. So the y terms drop out, and when I add these other ones, I get negative 5z equals negative 15. So what I did was I added these terms and these terms. At this point, I have two blank spaces here and one here. So it's kind of like a triangle of blank spaces. I've got one here, and one here. You have to get that kind of a triangle to make this work. It doesn't necessarily have to be the x's and the y, but in this case, and in most cases, that's usually what I look at as I try and get rid of two of the x's and one of the y's. Okay, so now let's get those out of there, and I'm ready to back substitute. So looking at this equation, I can solve for z very easily. I would say negative 5z equals negative 15, divide by negative 5, and I get z equals 3. Okay, now I'm going to take the second equation, which is 3y plus 2z equals negative 3, and I'm going to put 3 in for z because I just figured out that z was 3. So I end up with 3y plus 2 times 3 equals negative 3, so 3y plus 6 equals negative 3. 3y equals negative 9, so y is negative 3. And then the last thing I'm going to do is I'm going to take this value of z, this value of y, and I'm going to put them up in the top equation so that I can find x. So I have x minus 2 times y minus 3 times z, which is 3, equals 2. So x plus 6 minus 9 equals 2. X minus 3 equals 2, so x would be 5, which means my solution is 5, comma, negative 3, comma, 3. X, y, and then z. Okay, let's look at a system of equations where I have more variables than I do have equations. I'm still going to do the same kind of process, which means I want to get an equation with an x and I want to get rid of the other x. So to do that, I'm going to multiply this by negative 2. So that's going to give me negative 2x plus 4y minus 2z equals negative 4. Now I'm going to keep one of the two equations, and I think I'll just keep the top one as is. And now I'm going to replace the second one with the sum of this second equation and a multiple of the first equation. So to do that, the x's are going to drop out. I end up with a 3y, a minus 3z, and a minus 3. Okay, now at this point you might notice that there's a common factor of 3 here. So if you wanted to, you could divide, you can always do this, you can divide through by a number. I'm going to divide through by 3, so my system is going to change just a little bit. X minus 2y plus z equals 2, and then I'm going to end up with y minus z equals negative 1, because I divided all the way through by 3. Okay, now I can't go any further. I've got this blank spot here, but there's no way for me to go any further. So what I'm going to do is I'm going to let z be some arbitrary number a. and then I'm going to use that to back substitute. So my second equation here was y minus z equals negative 1. Well, I'm going to put an a in here so that it's y minus a equals a negative 1. And then I'm going to solve for y by adding a to both sides. If I add a to both sides, I get y equals a minus 1. Okay, so now I have got a value for z and a value for y. So I'm going to back substitute one more time to find a value for x. So I'm going to take that top equation, x minus 2 times y, but I'm going to use this for y. Y is a minus 1. And then I'm supposed to add z, and I know that z is also has a value, that's a. So I'm going to put an a in here, and then it's equals 2. So I substituted this for y and this for z. So I end up with x minus 2a plus 2 plus a equals 2. I'm solving for x. So if I put my two a terms together, I get minus 1a plus 2 equals 2. If I subtract 2 from both sides, I get 0. And if I add a to both sides, I get x equals a. So the solution for this problem would be x, y, z. So the x coordinate is a, the y coordinate is a minus 1, and the z coordinate is a. Which means I can take any number I want and put it in there. So let's let a be 7. If a is 7, then my ordered pair is 7, 6, 7. This is my a, this is a minus 1, and this is a. What that means is this particular point is a solution for this system. And I could let a be any number I want to, and I will get another point that is a solution to this system.